Hey, and welcome back everybody. Another exciting video in the Blue Glow Electronics Audio Tube Amp 101 series of lecture videos that I'm doing. This is episode 3, and today we're going to cover voltage, current, and resistance. Just a few things to note before we dive into it. One, there are a ton of videos out on the internet, on YouTube. There's a lot of websites that describe these exact concepts. And so you might ask, why would you watch this versus one of the others? What I'm trying to do with this series is make this stuff very practical and use real world examples. I'm trying to use tube amplifier examples in the descriptions and whatnot. So hopefully you'll learn voltage, current, resistance, and understand how it relates to tube amplifiers is what I'm trying to do. Just like the previous video, I'm going to stick with what I would call a technician level of math and physics and not get deep into the engineering. If you want to get deep into that stuff, go watch some other videos, lots of websites out there. Learn more. Hey, and if you can't understand what I'm showing you in these videos, go watch some of those others. And then come back and just pick up on the pieces where I'm trying to relate this stuff specifically to tube amplifiers. So let's dive on in and I'll show you a few concepts here. Okay, just a couple simple concepts and we'll get you moving right on along to understanding electricity. How many times have you walked across the room, touched a doorknob and got shocked? Or maybe combed your hair and your hair stood up everywhere? That's a concept called static electricity. And what's happening there is you have little balls, basically of electric charge, that are being stored in something. And then when you touch the doorknob or whatnot, you're releasing them from your hand to the doorknob. And what you're doing then is causing, you're actually having those balls of charged electrons actually flow from your finger to the doorknob. So for our little session we're going to do here, these balls, we're going to use them as charged electrons basically to represent. So let's pretend that you had a board, and this board was equal height on both sides of the board. And this is where we're starting to use a little bit of what I would call physical representation that ultimately we'll have to translate into this electrical representation, but it's a good way of getting around the concept. So you got a board here with these charged electrons sitting on the board. Both ends of the board are equal. Well, guess what? These balls do not move. They sit exactly still. So if you went out today and got about 10 tennis balls and put them onto a long board and stood there and got it perfectly even, the 10 tennis balls or golf balls, whatever you use, would sit exactly still if there was no difference in the height on both ends of this board. However, if you took one end of the board and lifted it up higher than the other end of the board, as you can see here, you would then have a term we call a difference in potential. So this end of the board right here would have a higher potential than this end of the board that's, let's just say, sitting on the ground. If you did that, guess what's going to start happening? You probably have it right. The balls would roll off of one end of this. And we'll show you that here in just a few minutes. But let's talk a little bit more about differences in potential. So that's how we actually measure a unit called volts. And volts are one of the fundamental principles you've got to learn. Volts, current, in other words, amps, and resistance are the three most fundamental things you need to learn. If you can grasp those, the rest of this will get pretty simple. So let's just say we had a board here and we held one end up at a height of 3. And in this case, we're going to call it volts. And we had another board that we held up here at a height of 1, and we would call that 1 volt. So it would be easy to determine that this board had 3 volts of potential or more potential than this board did, because this one is raised higher. And take a guess. Would these balls here not roll off of this board faster than these balls would roll off of this board? It's a good assumption if that's what you're guessing. All right, this is another concept you've got to grasp. Can be a little bit tricky, but let's just say we had this board, instead of sitting on the ground, we had it 2 feet up in the air. So you had a friend holding one end and you were holding the other end, exactly equal, 2 feet off the ground, and then you raised your end up to 5 feet off the ground. Well, that is the exact same 3 volts of potential here difference that we had in the previous slide, where one end was sitting on the ground and the other one was 3 feet in the air. Still 3 volts of potential. Similarly, let's just say you were able to hold one end of the board up in the air 22 feet and the other end of the board only 21 feet in the air. You would have 1 volt still of difference in potential between the 2 ends of the board. So 5 feet here, 2 feet here, 3 feet, or in this case, we're going to use electrical representation, 3 volts of potential energy between the difference in these ends of the board. Let's make it just a little bit tougher here. Let's just assume that we were able to hold one end of the board 2 feet below ground, maybe into the water or something. And we held one end just 1 foot up in the air. You got it. The difference in potential is still only 3 volts. Same here. We held one minus 8 feet and the other minus 7 feet. The difference is still only 1 volt in potential. I know this sounds silly right now, but you would not believe how many people later on down the road are working inside of a tube amplifier and they cannot grasp this concept. That if you had, let's just say this end was at 100 volts and this end down here was at 97 volts, that the difference between them is really 3 volts. And thus whatever is going across that board is 3 volts. Sounds simple, but people mess it up all the time, I promise you. So just as we promised earlier, if you have a difference in potential, as we showed, guess what happens? These balls or these electrons start to flow, and they flow very fast. And so guess what? There is also a measure of how fast those balls flow across any given point in time for 1 second. So let's pick anywhere along this board, and if we put a measure there and we started counting the electrons flowing past, when this number here, and it is a really big number, 6.241 times 10 to the 18. Pull your calculator out, do that. It is a huge number. But when that number of electrons flow past a given point during the duration of 1 second, we're going to say that equals to 1 ampere or 1 amp of current flow. And it's just a basic fundamental law you'll have to understand. Could go into days or weeks worth of physics that explain why that is. But for this technician level course, we're going to just have to assume that we understand that. So just know that a certain number of these flow by a given point equals 1 amp. And we'll talk about that more here in just 1 second. Another concept we've got to learn here is called resistance. So if we applied this red layer on top of our board here, and this red layer was, let's just say something like tar or honey or some glue, and then we raised this thing up so that we had potential on one end, more so than the other, the balls would start flowing, but because we've got this red substance applied to this board, the balls would flow much slower. So this concept is called resistance. Anytime you use something in electronics to slow down the flow of electricity or slow down the flow of current flow, we will call that substance a resistor. In other words, it's resisting. And the whole concept would be called resistance. Okay. We're going to measure this resistance in a unit called ohms. And we represent the ohm sign here with the omega symbol. So you could just write 1 ohm, or you could write 1 omega, which would represent ohms. So keep in mind, at this point, we've learned 3 units of measure. We've learned volt over here. We've learned ampere, or A, here for the current flow. And anytime you slow down that current flow, that's resistance here. And we measure that in ohms. All right, hope you're hanging with me at this point. If not, watch my video again. Go watch some other videos on the same topic. There's lots of different ways to represent this. I'm using this balls on the board analogy. But this is a fundamental law that we have to learn at this point in time. It's actually not a law, but it's a relative relationship between volts, current, and ohms. But it's actually called Ohm's law. Mr. Ohms, somebody many years ago, created this law, and it's stuck, and people have used it since then, and it works. What Ohm's law states is that you will have 1 ohm of resistance when it takes 1 volt here of potential to cause 1 amp of current flow. So basically 1 volt causes 1 amp of current flow would equal to 1 ohm of resistance. It is the fundamental relationship that all things going forward are based upon in electronics. So got to learn this one. And another way to represent this is to say that volts equals to current times resistance. Not going to get into the physics behind that. You just learn it, know it. And if you go back to episode number 2 I did some math equations using algebra, and if you'll remember, I used this V, I, and R, and we showed how you could move the R to one side of the equation or the I to the other side of the equation, and we did that just to show you the relationships between these things. Now you understand why I use the V, the I, and the R. And if you'll remember, we used V is equal to I over R. I also showed you the algebra that would let you know that I is equal to V over R. And the resistance equals to voltage over current. If you can get that concept down right here, you're home free for 99% of all the electronics we'll have to learn going forward as part of this tube amp series. Let's dive into a little bit of real world practicality of how you might use some of this stuff working on a tube amp. All right, let's get practical here. So you probably use one of these in your life. It's a D-volt battery, or D-size battery. Just good old battery made by Energizer. C-size, A-size, AA, AAA. They're all 1.5 volt batteries, believe it or not. And I've done a little bit of modification of this battery, and you can see here I've done nothing more than tape some wires onto to both ends of it, just to make it easier for me to connect my measuring points to it instead of having to hold them on the end of the battery. But outside of the tape and the 2 pieces of wire, this is a standard battery you can buy at any grocery store. So what I've done is I've connected the negative terminals to all my measuring pieces of equipment here to the negative side of the battery, and if you'll notice, it'll say positive right here. And it's just implied that the other end is negative. But if we grab this test lead here and drop it onto this end of the battery, if you'll notice over here, what do we get? Oh, it says 1.601 volts. Well, guess what? These things, even though they say they're 1.5 volts, they can range anywhere from 1.6 maybe down to 1.4 volts. It just means a good new battery should be at least 1.5 volts. Sometimes they have a little more oomph to them than that, and that's okay. Most of the devices they connect into are well aware of that. So this device is putting out 1.6 volts right now. You can see here. If I disconnect that device, and let's see here. I connect up an old analog meter here, it'll start swinging over, and on the scale that it's on, this top scale here with 50, 100, 150, you can see it's right here at 1.6 volts. So many ways to measure this thing. If I come up here to a little Rigol oscilloscope that I have, this line represents ground basically. And then when I connect the probe to that line, to the wire, what happened? It jumped up, and it jumped up by a specific amount. It's kind of hard to see the gradients here, but it went up by 1, and then if you did the measurement here, it would be 0.6. So from here to here, it went up 1.6 volts on that scale. Similarly here, trusty old Tektronix 2246 scopes, one of my favorite scopes of all time. It's an old school analog scope, whereas this is a modern new digital scope, but this thing's hard to beat. Alright, I thought I'd turn the lights off here so you can see it a little better, but when I connect, what happens? It jumps up, and then lo and behold, the little measurement here says it's about 1.56 volts. So roughly 1.6 volts here. So it gives you a good idea that we're able to measure voltage in many different ways. Okay, let me show you what I got going on here. I've got a 250 watt 8 ohm resistor here made by Dale, which is a really high quality resistor. However, this one got pulled from production wherever it was being used because it's no longer 8 ohms. It's creeped up just a little bit over time, and I measured it. It's 9.7 ohms. It's probably why whoever pulled it out of production did, but for most of the work we're doing, that's pretty darn close. And I actually have 2 of these units mounted inside of this chassis here. You've probably seen me use this in many of my videos, where it is my dummy load for left channel and right channel, and it's what I do all my measurements off of. So what feeds that here is the outputs, and if you'll notice where those connect, they connect straight down here into whatever I'm measuring, a tube amplifier or solid state amp or whatever. So basically these leads go straight up into this dummy load unit and connect to one of these. So there's one of these for each set of leads, and then just like here, I've got little connections coming off of them that'll allow me to measure things, and those measurements then get fed to these outputs here that I'm feeding to things like my audio analyzer here, or up into the spectrum analyzer. Feed it over out of this red one here into my oscilloscope. So really I'm just measuring off of this dummy load, and all these measurements I'm taking when I'm working on electronic equipment like this, they all go straight back to Ohm's law. You know the fixed resistance of these resistors. The 2 I put inside of this unit are pretty darn close to 8 ohms. I've had about 30 of these things I picked up along the way somewhere, and I went through and hand selected some really good ones for that dummy load. But that's really all I'm doing is you know, some known values. So let me give you an example here, and we'll do a little demo real quick. So let's just say you're playing your stereo to your outputs, which would be your speakers, which are typically just like this, 8 ohm devices, and you were able to put a set of you know, measurement leads off of a meter across the outputs of your amplifier, which is what I do with that dummy load setup up there. But similarly, I've got the exact same thing set up here. If you'll notice, I'm actually using a power supply here that right now is providing, you see this thing's variable. I can turn this knob and I can adjust the voltage down or up. This meter on the front's just kind of a relative meter, but if you'll notice, coming out of this meter I've actually got a BNC connection here that feeds over here into this really nice flute meter that stays on the bench here. And if you'll notice, as I turn that knob over here, I'm able to adjust it up. Let me get it at 9.7 volts, somewhere thereabouts. Thing's really tricky to get it to stay still. somewhere along in there. So you can see here on this meter, hey, we're not bad off, 9 point something there. And so when we come back down here, I've actually got the wires coming out of that power supply flowing through this meter here so that I can measure the current, and this is the other end of it. So when I connect this to the actual resistor, what do I end up with here? I end up with 0.97 amps, pretty darn close to 1 amp. And so 1 amp, I see why the thing's kind of dropped back down. Let me get it back up here a little bit. So we're at 9.6 volts across a 9.7 ohm resistor, and we're getting here 0.99, basically 1 amp of 1 amp of current. So Ohm's law holds true. So if you'll remember, I is equal to V over R. So 9.7 volts over 9.7 ohms was equal to what? 9.7 divided by 9.7 is equal to 1, and we're pretty darn close to that over here on the 0.98. As you can see in electronics, these measurements I'm doing, they rarely get exactly precise to where you've got exactly, 1 volt. It's pretty darn close. We're at 0.99 and 9.7 ohm resistor. So it should give you an idea, though, of how, a practical measurement. I'll show you, give you an example here. So if we were playing music through this amp and feeding out of it up into the dummy load, which had one of these resistors, and let's just say that you measured, 8 volts coming across an 8 ohm resistor, right? Well, then you would know that you were putting out 1 amp of current through this amplifier coming out the outside. I mean, that's a very important measurement because as I think I showed you last time, there was a power formula that we used, and power is equal to V squared over R. And so if you took V squared, 8 times 8, right, 64 divided by the resistance, which is 8, you would know then that you were putting out 8 watts of power at that point in time. So it's not a bad thing to learn these good old Ohm's law basic fundamentals. Let's do a little bit of measuring inside of this. I'll give you an example or two. All right, you may remember this from last time. So I'm measuring the potential voltage. Remember, I've got one end connected to ground here. So this one's at 0 potential volts. And the other end here, connected right here, is also at 0 potential volts. And if you'll read my DC voltage, it's 0.0001 millivolts. So just a teeny little bit being picked up, probably through this wire as an antenna in the air here. But if I move to the other side of this wire, you'll notice here I've got 10.76 volts coming through this thing. Let's do the math on that real quick. Alright, if you do that 10.76 divided by, this is a 150 ohm resistor, if you can read that on here. You do the math on that, it comes up, it's about 71 millivolts of current actually flowing through that resistor right now. So, and it's flowing through one side, going to the other, going to ground at this point in time. Let's find a few other points to measure and give you an example. Okay, notice I've got one end on ground here. The other end is right here on the other side of these two resistors, which is actually where the red wire coming off of this capacitor down here comes from, otherwise known as the B+. It's what's feeding the plates on the top of these tubes. And if you'll notice, that is sitting at 353 volts right there. So just a little word to the wise, 353 volts is enough to kill you. You'll never ever want to put more than one hand inside of something like this when you're measuring at a time. You need to take the other hand and sit on it or keep it way out of the way. And the reason for that is you could you yourself can become a conductor for electricity to flow to ground. So if your right hand happened to touch that and your left hand was holding the chassis here, then those 353 volts would flow through your right arm, straight across your chest, through your heart, and out the left arm and back through this, and it's surely is enough to kill you. You just don't want to create a return path through your body to ground per se. Alright, I picked another place inside of this amplifier, and this is on the plates of the 12AX7, 12AU7 tubes. If you'll notice, they're running at 221 volts. Not nearly as hot as these power output tubes that the 6BQ5s or EL84s in the outputs here. So as you can see, throughout an amplifier chassis, there are many different voltages running around and different potentials per se. So let's go jump to a schematic. I'll show you a little more. Okay, this is actually the Pilot 232 amplifier that we had on the bench a while ago. This is the schematic for it, or one piece of the schematic. This is actually the power supply schematic. The part that ultimately provides voltages throughout the amplifier so that it operates properly. And different parts of the amplifier need different operating voltages, in other words, potential voltages, to be effective. So this power supply is not much different than the power supply I had up on my bench earlier, where I was creating the 9.7 volts with. This one, what it does is it through the use of this transformer here, it takes what comes out of your wall outlet and basically converts the voltages to different voltages to then be fed through this rectifier right here. This rectifier is called a GZ34. It's a vacuum tube, otherwise sometimes known as a 5AR4 vacuum tube, but it's a really good vacuum tube used in a lot of vintage electronics to basically convert alternating current into direct current voltages. And you'll learn more about that in upcoming episodes when we cover AC and DC. But just know that all the voltages we've been dealing with today in this video so far have been DC voltages, direct current voltages, and that's what we're talking about here in this video. So the transformer feeds the correct voltages into this rectifier tube. This rectifier tube then produces a potential voltage of 370 volts coming off of pin 8 here of this tube. And if you'll notice, that potential voltage, if you compare it to this potential voltage, so anytime you see this little symbol, and you'll see it a lot of times, you can see it just 4 or 5 times here in just this one schematic. Anytime you see those symbols, that is the symbol for ground. It stands for 0 volts potential, and 90+% of times, almost all the time, but not every time, the chassis of an amplifier, the metal chassis, is also at ground or 0 volts. In other words, that chassis is what you're using as your 0 volt reference, and it also is fed through your house wiring back to actual earth ground. So if you remember today, I connected the black lead of my voltmeter to the chassis itself. That's what I was connecting to right there, was ground or 0 volts potential. I then connected the other lead on that meter to several different points, and when I did, I was measuring the difference in potential between ground and these other points inside the amplifier. So coming out of the rectifier, this thing starts out with 370 volts sitting right here on that node. If you'll notice then, this 370 volts ultimately through these various connections here, through this series of connections, by coming over and then going up and then turning and going over here, going through here and through here, this thing feeds various voltages to the amplifier. So how does it get differing voltages other than 370? Well, We get that by using what we talked about today, the concept called resistance. Otherwise, how you get resistance is through a physical device called a resistor. And this little symbol you're seeing right here with the squiggly little straight lines here, similar to this one, and this one, and this one, and this one. Quite a few resistors. Oh, and one more down here. Quite a few resistors in this circuit. So when you look at a schematic and you're starting to say, hey, what do these things do? All these various little devices. Well, heck, I've already showed you here in this video what 6 of these little components do. Their purpose is to slow down current, or in other words, drop voltage. Because if you did Ohm's law on it, current current times resistance is equal to voltage. So in this case here, what we've done is we've taken 370 volts and we've dropped it down to 350 volts. And we did that through this resistor right here. Similarly, if we've got 350 volts up here, well, that point on this schematic is the same as this point, is the same as this point. We've got 350 volts sitting all along here and all along here, right? And then we take that 350 volts, drop some of it across this resistor, and it gets us down to 225 volts. We take that 350 volts that's sitting here, and we drop it through this resistor, which by the way is the same as at this point, which is the same as at this point. Why? Because that resistor value and that resistor value is the same. But then you take and drop that amount across this resistor, and you end up at 150 volts here at this point. In other words, the 350 volts right here dropped across both of those resistors yield you 150 volts left over. Which means that somewhere along the line here, we lost 200 volts across these resistors. And that's what their purpose is. That's not a bad thing. It's why they're put in place. That's what they're designed to do, is to use to drop voltage. Similarly, we had right here, 225 volts. We drop it across another resistor and end up with 145 volts here at this point. And all these voltages are in reference to what? Ground here. So as you can see, this whole power supply's purpose in life is to create these source voltages to feed varying other points inside the amplifier so that they're operating at just the right voltages to do just the right things that they're supposed to do. And you'll learn a lot more about that in subsequent videos. Okay, we've now moved to another part of the schematic, and these are the output tubes right here. And we've shown you that before, EL84 output tubes. This right here is the audio frequency amplifier, the 12AX7. And if you remember, we had all those source voltages being fed by the power supply earlier. Well, if you'll start noticing, right there's one of those source places that it feeds to. The 350 volt source connects right here. If you'll notice, the 225 volt source connects right here. So those feed points, source points in the other part of the power supply feed to this part of the amplifier to create the right operating environments for these tubes to operate properly. And let's take a look at a few voltages that are inside of this tube amp. So if you measured relative to ground, this point right here, which happens to be the plate, this top little symbol, you'll start to learn some of this. This little symbol right here is the plate of this EL84 output tube. It measures 345 volts relative to ground. Hey, that's a lot of voltage. So you'll get used to seeing, when you look at the plates of tubes, there's an awful lot of voltage sitting on those, and that's what those plates need to operate properly. You'll learn more about that when we get into how tubes work. Another place you'll see, look at this little space right here. This with the 3 little broken lines, that is called the grid of this tube. And what voltage is the grid operating at? Wow, check it out, 0 volts. And that's fairly common in amplifiers. You'll see the grids somewhere around 0 volts in an amplifier. And then this bottom piece right here, that is called the cathode of a tube. And if you'll notice, this cathode is sitting at 10 volts right here. Well, if you'll remember in that amplifier we were looking at a while ago, when I connected to one side of that resistor, I was connecting actually right here, because this is the resistor, that 150 ohm resistor that we were connecting across. In this case, I changed it in the schematic, shows 120 ohm. I've actually changed it to 150 ohm in that amplifier, and I'll explain in another video as to why I did that. But so connected on one side of the resistor right here, which is the same as connecting right here. I had 0 volts, if you'll remember. If you'll remember, I connected the other side of that resistor. I had 10.76 volts, I think it was. Well, that point and this point are all the same, because the schematic wires just connect together. And if you'll notice, it shows 10 volts, which is roughly what we had sitting there. If you'll notice this point here, 0 volts relative to this 345 volts, that's a pretty good difference in potential right there. And one of the things you'll learn later when we're talking about biasing tubes is that you have to create a negative potential on the grid relative to the cathode here. In other words said, the cathode has to be at a higher voltage than the grid, which is the case here, 10 volts to 0 volts. So in retrospect, the little cathode, the grid here is at a minus 10 volt potential relative to the cathode. And don't worry if you didn't get that. We'll do enough along the way. You'll keep grasping it as we go along. We'll show again over here. 145 volts sitting on top of this tube right here. What have we got here? The cathode of this tube sitting at 1 volt. You can see right here, 1 volt. We also have the grid setting at 0 volts. Similarly, the grid is negative in potential, in other words, less voltage than the cathode, which is what's required as we go to bias this tube, and you'll learn more and more about that as we go along. As you can see in this thing, lots of resistors here. What are the purpose of these resistors? They're to take voltages like this 225 volts that's sitting right here and to drop it from 225 volts down to, what does it drop it to as it goes across here? 145 volts. Just keep in mind, that's the purpose of resistors here, is to drop voltages so that you can set the right operating parameters that a tube needs to operate effectively. Guys and gals, I hope this is starting to get you familiar with looking at a schematic. Next time we'll talk about a few more things. Don't forget, we've already learned what all these things are right here. What are they? They are ground, and you see them all throughout schematics. So now when you look at a really busy schematic, you can say, hey, I know what all those little things are. Those are ground points or 0 volts potential. You can also come along and say, hey, you know what? These resistors, I see them all throughout this amplifier. Look at this. I can't even begin to count them here. How many resistors are in this thing? Up here's another one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 resistors right here. You know what every one of those resistors' purpose is. It's to drop voltage from some given point to another point to get the voltages where you want them within the amplifier. So if you look at this whole schematic from one end to the other, heck, you've already figured out what probably 3/4 of the components in here are and what their purpose is in a tube amplifier and in the design. All right, thanks everybody for watching. Hey, I love the feedback you're giving me. Keep throwing it at me. I'm going to try to keep these videos to about 30 minutes going forwards if I can. Seems to make them a little more digestible. Going to keep using some interactive technologies like I'm using here, and hope you learned something. And the next video we're going to do, we're going to dive deep into resistors. So we're going to talk about resistors, we're going to talk about conductors, or in other words, wires, and we're going to talk about insulators, things that protect you from voltages and whatnot. So you'll learn everything you'll ever need to know for the most part about resistors in the next session. Hold tight. Thanks again, everybody, and we'll see you soon.